Okay, so previously we learn on AC response, or you can say that the frequency response is what we have learned. In frequency response, we are interested in two kinds of responses. One is called magnitude and one is called phase response. Combining these two is going to tell me whether my system is stable or not. Stability is depending on one fact, phase margin. If it is greater than 45-degree, you are in the safe zone, or you should make sure that the time constant is good enough to give you the output before the state is changing, right? So like it still it's in ringing, but it's changing the state. So even though 45-degree is there, even the phase margin is 45-degree, but that's not good enough. So then you have to actually change the bandwidth, or you can say that the pole location. If you keep the pole location little bit higher, then this will be taken care, right? So this was the thing we learned. The next topic is on, actually the name of that topic is studying the RC, RL, and RLC circuits using Laplace transform and step response. But I learned that there are some, like if I spend some one lecture, maybe it will be useful to understand other things rather than going from Laplace. Let's start from differential equation, which you have studied already. If you are getting in any difficulty, you can go through the differential equation of this this book. I follow this book. This is the most ancient one. This book, which I kept it here, it's a 1961. The copy, second edition. First must be in 1941, and everybody have copied from there. This is what I learned from my teachers, and I also learned that other books, which we found out, all are copied from here only. This is the most oldest book. So it's in, like you can see, it's 1.5 pound. Earlier time it, okay, visible, right? So soft copy is also available, and we have almost like 50 copies are available in our library, as our exam is open book. So remember to keep books with you, right? If you want to issue it, you can issue it. Then another book is also very famous book, Emmy Walkenberg. This is also available in our library. So they are also around same range, around 40-50 books are available. So everybody can have one book. Yeah. So you can use any one of the book, or maybe both the books. I am going to generally teach from the first book. Okay, and we'll solve some of the questions available in both the books. So it's a combination of both the books which we are going to solve. In examination, I am going to keep something out of this, right? Not from these two books, but I'll think and I'll keep some new problems for you. So it will be designed by me, right? Okay. Right now, what we are studying is like word by word. I'm teaching chapter 5, network analysis 1. This is the only thing I'm teaching. There is no other thing coming from anywhere else. Okay. So before going to anything else, let's learn one thing, which is called, do you understand all of these things? Yes or no? So what is the meaning of all these things? T equal to 0, T equal to 0. Hmm? Okay, just after 0. And so these are the different time instances after which the network or whatever the elements are there which are working on. So at T equal to 0 minus, the switch is off, but at T equal to 0 or maybe 0 plus, the switch is on, and you are looking at the response of this the output. When I'm saying response, it might be any kind of response, frequency or transient. If you are interested in frequency, any chance in frequency, then you should go to Bode plot, right? But if you are interested in time response. We are not going to call it time, but we are going to call it transient response, right? Because it's with respect to time, it's a toggling, it's a ringing, so we are calling it transient response. So all the simulators, I'm talking about simulators like spice or other spice based simulators, they are going to call transient response or the transient analysis, under which you are going to do the time analysis. So they don't call it time response, but it's transient, but both are same. But there is a thin line between time and transient, because transient is the one when it's toggling and then it's settled. So this part is actually known as transient, but simulators call everything as transient. In simulation we have transient analysis only, right? So let's look into the network. So if your circuit is linear, what do you mean by linear, by the way? Very quickly, Kathy, what do you think? Linear? Okay. This is something like, yeah, Kathy. This is graphical representation of linear thing, right? Or you must have studied this, where c equal to 0, by the way, right? Other than mathematics in circuits, or do you know any other definition of linear that follows superposition? You are saying something, Ohm's law or what? Superposition, yeah. Maybe you are linking with v equal to ir, right? So as Divanshu is saying, superposition theorem and homogeneity, right? If you are following both the uh, both the principles, then the circuits, that circuit is linear. Otherwise it's non-linear. So what do you think about inductor? As Piyush told about Ohm's law, v equal to ir, resistance is linear. What about inductor? Is it linear or non-linear? What about capacitor? What about transistor, diode? So why we are studying linear? So this is the title. You must have implemented superposition theorem, Norton and Thevenin. All these theorem you have applied, but there is one condition. Those are only applicable to linear circuits. They are not applicable to any non-linear circuit. If it is non-linear, the rules are different. Then you cannot follow this. You need to follow something else, maybe Taylor series, or maybe through Volterra series you can derive some different set of equations. But for linear only you can apply those theorems: superposition, Thevenin and Norton. So what do you think, how we are applying this inductor, capacitor, transistor, diode, all these things for like superposition, Thevenin and Norton? So are these theorems applicable to these non-linear devices also? Gaurav, what do you think? You agree with me, right? That is what you have studied with the star on top, that all these theorems are only applicable to linear circuits. Superposition, if it is not linear, then you cannot apply superposition at all, right? You must have studied superposition, homogeneity, all these things in signals and system, right? There you are saying that system is linear, then and then we can apply it. And you must have written that if there is an LTI system, right? You've seen this word everywhere, linear time invariant. Still you are applying it, and internally these systems will have inductor, capacitor, transistor, diode. Even if they are not there, parasitic resistance, parasitic capacitance, inductance, transistor, diodes, all are there. So the system is actually non-linear. So how we are doing this linearity thing? What do you think? So what all engineers thought, rather than doing analysis which is the full system, let's say there is a system which is like this, let's say input versus output, this is non-linear system. But if I want to apply my theory of linearity, what I'm going to do, I'm not going to treat the whole system as the one system, but I'll make them in pieces, like one piece is here, one piece is here, and one piece is here, one piece is here, right? I'm breaking it in small pieces, and I'm going to analyze from 0 to, let's say, till some v1, then till some v2, then till some v3, because internally from 0 to v1 for a small value it's linear. This kind of approximation is known as piecewise linear, right? So this is what we are doing, and we are following this principle that it's non-linear, but I'm going to only take care of small part, and that is how we are land up in small signal models. We are not interested in large signal which are going to keep the things in non-linear mode, right? Have you heard this word small signal? Okay, for transistors equivalent small signal model which has only resistances and capacitances, right? And some current sources or maybe voltage sources, those are dependent voltage and current sources, right? So that is what we are doing. So with these assumption, I am asking, I am having a linear network which has inductor, capacitor, whatever you want to keep it, but I am going to do the analysis for piecewise linear only. And in that case, if I have so many, like this green colored are actually the voltage sources which are independent voltage sources, and these blue colored ticks are actually the independent current sources, and I am going to take output from this impedance. Then how I am going to solve this kind of circuit? I am going to use superposition theorem, and superposition theorem, it's a revisit of superposition. So all the voltage sources are short circuit. So voltage sources are short circuit, are zero, and all the currents are open circuit, and I am going to only use one voltage or current source at a time, and I'll find out what is the output. Then I'll apply same thing for maybe different current voltage. I'll do one by one, and whatever the output I'm getting, the total current is equal to current because of first voltage source, current because of second voltage source, and so on with current sources and all. I'll add all of them, and that will be the total current flowing through the impedance at the output. This one. Any doubt in this? This is called superposition, right? Okay. Now let's go back to another thing. It's already known to you, but it's a revisit of what you have studied. So if there is an element called resistance, as per Ohm's law, I'm keeping, if it is small v and small I, all are AC signals, right? If they are in capital, they are DC signals. If they are like this, let's call, let's say V in, this is AC plus DC. Similarly, you can write down this way also. These are the standard notation which we are following. So right now, whatever we are following, it's AC signal, and it's moving with respect to time. That's why we are calling small v of t, small I of t. Both are the time signals which are moving and having some frequency components also. So v of t is equal to r I of t, and there is very famous thing which we are using generally. It's G. Do you know about this? It's transconductance. The unit of this one is either this one or mho or Siemens, right? It's reverse of ohm, so it's mho, right? Any one of them you can use it, right? What was spelling? I forgot. Okay. SIE. Okay. Right. Okay. Hmm. Anybody who is studying German? Studied German. Okay. In German, people are reading this Siemens, right? So, do you know how to read this one? Okay, maybe just for how to read this one, E or I. So the rule says that whatever is the last, you need to read that one. If it is like this, you need to read diesel. If it is like this, you need to read Einstein. Right? So that's why I get confused generally. Right? Huh? Sorry? Einstein's. Einstein, no? I wrote something wrong. Einstein. Albert Einstein, no? It's something else. Okay. It's a combination of, it's a diphthongs. It's a diphthong, right? So, right? Whatever is last in the combination of E and I, you need to read the last one. That is the rule. Okay. Maybe I forgot, then you can tell me. I studied in my school German and then I forgot most of the things. Okay. So, similar to that, if there is a capacitor, so if you are writing a current equation, I of t is equal to C dV by dt. So all electrical engineer will never forget about this I of t. If you are doing Laplace, you will never forget about V of s, right? So these notations are very important. Do not forget what is in bracket, because that analysis will tell you what analysis you are doing, right? So do not drop these things. Maybe you will feel that it's V only. V might be anything, either in time, frequency. So you need to denote which analysis you are using. Okay. So now the interesting part is that it's not happening in resistance, but in capacitor, when you are going to add V of t, it's 1 by c integration from 0 minus to t I of tau d tau plus the initial condition. If it is initially charged to some voltage, 1 volt, 2 volt, so it has to charge on top of that, right? It will not forget the previous condition, right? So it's a kind of tank. If it is previously filled, then whatever you are keeping, it will go on top of that one, right? So that one will be Vc of 0 minus, and you are adding something on top of this one, which will be 1 by c integration 0 minus to t and then I of tau d tau, right? It's depending on the dynamics of what capacitor you are using, and that will give you the integration time depending on the value, right? Okay. So right now we are not talking anything about Laplace. Okay. So maybe afterwards we are going to define that. So now, yeah. Now let's revisit inductor. In the case of inductor, we already know that it's L di by dt, right? And I of t can be written as similar to what we are writing in capacitor. Capacitor was remembering the voltage, so now inductor is the one who is remembering the previous current. It's a current storing device, and that one is uh, voltage storing device. Okay. Other than this, do you know anything else other than RL and C? Do you know anything else? I'm telling this because just for your information, something has invented in 2009. Anybody from like from back, my TAs? Do you remember? Himanshu, do you remember? So resistance, capacitance, and inductor. There is one more which was invented in 2009. Maybe Pranchi? No, something new. because I taught this to first year when I was teaching applied electronics. So if you remember, I taught memristor. Yeah, no, I taught them, not to you. So there is fourth missing. So just you need to type this one. This is a nature paper in 2009, and this was like in 1971. There is a professor called Professor Leon Chua. Some people call it Chua, but the real one is Chua, right? So CHUA, and that's the unit of memristor. What Leon Chua has thought, like he was thinking that so all the mechanical system has four fundamental quantities. One is level, temperature, flow, and pressure, right? Other quantities are derived from these four. Similar to our case, we have voltage, current, and charge, and flux. These four quantities, other quantities are derived from here. Whatever quantity is there, doesn't matter, right? Either it is resistance, capacitance. These are also the quantities which are derived from here. Frequency, anything, hertz, everything has been derived from these four quantities. Similar for this. So for measuring these four quantities, generally they have some meter. For if you want to go to level to temperature, you will have some meter. From temperature to flow, there is some meter. So similarly, we have some meters. So voltage to current, if you want to measure, then you are using resistance, right? This is the like sensor for us, which converts voltage to current, current to voltage, whatever you want. What about current to? I made it. If it goes this way, then it will work. So what about this guy? What? What about this guy? What about this guy? That is the fourth missing. And Leon Shua thought in 1971 he was, uh, if I'm not wrong, PhD from MIT or maybe Stanford. I just need to like check. But he told this is the fourth element, which is going to look like this one, and this element will be is equal to d phi by dq. It is a resistor, but it will remember also. And almost for 20-30 years people were in trying to find out this. So Leon Shua has contributed all the mathematics, and that mathematics leads to give you like there is a possibility to use it as a better memory device, right? But that was invented in 2009 using something called molecular electronics. It's not exactly what we are doing with CMOS. It's titanium dioxide. Through titanium dioxide, they have invented this. If you want to understand, maybe in chemistry, you can do this. And you can read about this paper if you want. And there are many people who are doing research on this. But till now, no product has came out. But maybe in 1 or 2 years, we are going to have one memory in HP laptops. We will have it. They took patent, and this is from HP people. So you can read about it, maybe more theory and how it has invented and what are the things. It's a big theory. You can see lots of videos on YouTube also. So let's assume that memristor will be there in future, but and you are going to use these equations also. So even if it will be invented, and it will be right now it's not in book because we are studying the book which is 1941, and we are talking about 2009. Maybe something has been invented maybe in 2019 also, and it's not known to me, but still you can apply all these differential equation theories on top of that with whatever the theories we are studying right now. So for known three circuit elements R, L, and C, you can write down the equation where first one is a resistance does not remember anything. Inductor and capacitor remembers current and voltages respectively, and memory star is the one which remembers the charge. So that is the theory of all of them. Now, okay, now there is a network which has RL and C. For your better understanding, we have kept the initial condition voltages with 0 minus for VC1, VC2, and I am going to do the mass analysis. You have done it, right? So there are three possible currents which are flowing and which are going to cover all the elements, and I'm interested in the output, right, across resistance. Now if I am going to write the equation, can you write down in your notebook at for mass equation for I1? So the first equation should be V1 of t minus, because VC0 minus is equal to R1 times I1 of t plus 1 by C 1 integration I1 of t dt minus I2 part also, right? Can you write down this? This is just for your, like, for your practice. Answer is already in given in next slide. Similarly, you can write down for this one. If you are finding two currents flowing from one element, you need to make the plus and minus. If you are doing the mass analysis for I1, then I1 should be higher than I2. So I1 minus I2, that will go to this equation, right? Right, for this element. If you are not getting same answer, please let me know. I can explain that. Right? This is just for your, you know, revision what you have done, whether you remember or not. Right now we are not interested in output. We are interested in three correct mass current equations. Right, Rohit? This kind of analysis is known as mass analysis. Okay. I got misguided by Rohit. Actually, he told me that he never studied mass and nodal analysis. So I kept these slides in the course. Anyway, still there are many people who forgot this, right? Like differential equations, we forgot, right? Okay. So are you getting same equations or different? You please write down and then we'll look at the solution. And if you have any doubt, please let me know, so that because we have to use these mass analysis and nodal analysis maybe every time. You cannot avoid it. We are going to learn even some advanced technique also. By looking at just network, you can write down the V out by V in. But we need to know mass analysis and nodal analysis. Yeah, Manpreet, fine, right? So this is the result for three mass equations. So this guy is old, so maybe he is writing in different way, right? Franklin Kuo. But the answer should be same. Like whatever you are getting, it has to be same.
Why the integration is from 0 minus to
Zero.
2 plus?
No, it's even from minus. Yeah, you can write down, but the reality says that you, like, minus infinity. Initial values goes another side, right? In voltage, it's there. When we are writing integration and differentiation equations, all will include initial conditions. You cannot avoid it in time domain. If it is frequency, when you are writing Fourier series or Fourier transform, all will add initial conditions. But if you are going to Laplace, there is no initial condition, because, as I told you, initial condition 0 means you are in linear domain. There is no problem, right? System is not non-linear. the system is linear, so then you can apply Laplace. Who is stopping you? And that's how this course has built on top of that, that everything is linear, let's apply Laplace. But I thought you will miss something if I am not going to teach differential. Generally all the electrical engineer everywhere, uh, in around the world, they are studying differential, Laplace, all these things in network theory. Unfortunately, we have some more topics has been given. That's why we cannot cover everything like thoroughly, right? But I believe you have studied in IC 160. This is what Urugundi sir told me, that he has taught all these things and you are expert of that. If you are getting any difficulty, you can contact me, right? But these are very easy thing, right? Now, so these are the, we are not interested in looking at the output, because afterwards it's just playing with the equations. Now let's assume that there is another analysis, and same analysis we can apply it to previous network also. But now I want to apply nodal analysis, which is in terms of voltages for this network. So can you write down how many nodes are you seeing, by the way? Two nodes, right? V1 and V2. Now can you write down what is happening at node V1 and what is happening at node V2? So G1 and G2 are transconductances. Right? If you are not writing and if you are already expert. So one side is current, where the initial condition of inductor is already included, and another side is the whole, like, the current equations has been written in terms of voltages, right? And one more thing, yeah, answering Piyush's question. So we are into the system which is causal. We are not into the world, like mathematicians can talk about all the abstract things, but when it comes to engineering, we are talking about all the causal systems. So causal systems occur here, not in previous one. We don't care for that even. But if you want to do it from minus infinity to plus infinity, ultimately you need to keep the real time, right? Just to get the correct answer. Okay. Okay. So let's relook at differential equations. It's okay. One more thing, after doing all these things, you have to play with the equation to just find out what is VO by, or V2 by I, or whatever you want to do it, right? Transfer function and all these things are possible. But before going to that, one more thing which I want to tell you. In differential, you are not only dealing with initial condition, you are dealing with initial condition, derivative of initial condition, even with final condition. Yes, when you are solving the uh, differential equations, you should have given with so many things: initial conditions, derivative of initial condition, and final condition, to find out the correct solution. And when you are solving the differential equation using mass analysis or nodal analysis, doesn't matter. When you are exciting your circuit with DC or sine wave, you may have differential solutions which might be complete and particular integral in CS or PI, right? There are two solutions, you are adding them afterwards. So whatever you are looking into complete solution, that is known as transient response or free response. Particular integral will tell you the force response. Whatever we are doing, it's happening at DC or sine wave excitation, right? With that input. But if you are doing in case of constant or periodic excitations, the force response, means particular integral at t equal to infinity, is known as final or steady state response. I'm telling you everything in terms of differential equation, right? So if you are finding something at t equal to 0 plus, and you may have some uh, condition. So that will be, if it is happening at DC or near DC, or with small value, it will be transient response or maybe forced response. But when it's going to be stable at t equal to infinity, when we are saying t equal to infinity, that's the time when you are going to see the response steady, means there is no ringing. If this is input, and if this is this time, after this time we are going to declare that one as t equal to infinity. Okay, so that's the philosophy. Infinity does not mean it's infinity, right? Okay. Okay, where I went. Okay, now let's look at the initial conditions for capacitor. Let's defining all these notations. So vc 0 plus, if you are going from t equal to 0 minus to 0 plus, in between this time, whatever is happening, like I of tau d tau plus vc of 0 minus, that is going to give you the initial condition of capacitor. Sorry, the final condition, because it's 0 plus. It does not mean. Okay, one more thing, it is with assumption that this I of t does not contain any impulses or derivative of impulses. What do you mean by this? What do you think?
It means that IT is continuous.
Yes. So
So we can perform a continuous integral from 0 minus to 0 plus. We do not have to break it.
but what is the advantage of writing this line? Because with line this is going to happen.
Yeah.
This is the test to find out the vc 0 plus and vc 0 minus. I'm interested in vc 0 plus and vc 0 minus if this part is going to be constant. When it can be constant?
Zero. It should be zero only, no?
It might be some other value also. Still we are in, it may not be 0 all the time. Maybe when we are going to solve the like circuits, then you will understand what I mean to say. Okay, let's look at this, which has only resistance and capacitance, right? So this illustration is also copied from, like, I'm following, word by word what is written in Franklin Co, so that there is no discrepancy in understanding, right? And I'm speaking what Co has told. I also read that. Okay, so consider the RC network shown in figure. I removed the figure number so that, right, it's suitable for my presentation. The switch is closed at t equal to 0, and we assume there is no initial charge in capacitor. Let us find the initial conditions I0 plus, I0 minus for the differential equations for the circuit, which is V u of t. Now, do you understand what is u of t? What is that u of t? It's step. What is impulse?
Delta T.
Delta of t. Right? So, V with u of t, he is talking about u of t because earlier the switch was off, so here 0 volt was available. When I switch it on, this voltage will rise, and it will look like a, a step response, right, or the step input to the capacitor's positive plate, right? That's why we are calling it V of u of t. V times u of t is equal to R times I of t. I am again applying a mesh analysis, plus 1 by c integration going from 0 minus to t I of tau d of tau, right? Now what is happening at t equal to 0 plus? T equal to 0 plus, what is going to happen? Whether it's this capacitor will act as a short circuit in terms of current. Just look at this. Yes or no? In terms of voltage, it will go open. It will block DC voltage, not DC current, right? So it will be short, and you can write down directly I0 plus is equal to, can you apply for this network? V by R. I'm applying just Ohm's law using mesh analysis. So it's V by R, that is going to give me I 0 plus, because I'm applying this at t equal to 0 plus. Now I'm interested in the part I derivative of 0 plus. So in that case, this was the first thing. When you are doing this, if you are making the derivative of the previous equation, which was v u of t plus r I of t plus 1 by c integration from 0 minus to t I of t d tau, right? Then when I'm going to take the derivative of this one, I'm going to see this equation, because v delta of t, right? We understand what is impulse, right? Delta direct function, this is equal to r I prime of t plus I of t divided by c, because it's a derivative. At t equal to 0 plus, it's equal to 0, because it's a small time and thereafter it's 0. It's delta of t at t equal to 0 minus, it's going up and coming back also, but at t equal to 0 plus, it's 0. So that is what I wrote it here, is equal to r I prime of 0 plus plus I 0 plus divided by c. This is already known to me. When I'm going to keep it, I'm going to get I prime 0 plus is equal to v by minus r square times c. Are you following this? Or if you want, we can solve it without looking at this. Are you following? Okay. Now the next question is the final condition, which is happening at infinite thing. So at infinite, what is going to happen? This is going to be open circuit. If it is open circuit, there is no current. So at infinity, the current is 0. But if you are interested in nodal analysis, the entire thing will be reverse, because at infinity capacitor gets short, and at 0 condition capacitor gets open. So the equation will be different. V 0 plus is equal to actually 0, and at infinity you are going to see I times R. If you are writing in terms of voltage or nodal, if you are writing in terms of current, the answers are different. Just look at that. Are you following, or is it too fast? Okay, so similar to what we have learned in voltage, if it is current, you will have a previous condition coming from current, which is IL 0 minus, and similar thing we are writing, if Vt does not contain any impulses, then VL0 plus equal to VL0 minus, because that is what we want to do. So then it will be some zero value. If there is no initial current, IL0 plus equal to 0, and similarly IL0 minus is also equal to 0. This analogy can also be obtained from fact that the current through an inductor cannot change instantaneously due to the conservation of flux linkages. This is already known to you, right? Anything which is not known to you, just let me know. Today's lecture is revision, what you have studied, IC 160. That's what I'm saying. If you have any difficulty, just let me know. Okay. If no difficulty, let's apply same thing here. Can you tell me what will be the I0 plus? At 0 plus, what is going to happen to inductor? Short or open? Then it has to be 0, right? 0, no problem. What is happening at higher value? If you want to find out at infinity, it's a short and it's V by R, right? It's also very easy. The only thing is I want to find out I prime of 0 plus. If I want to find out the derivative of that, I need to take derivative of the first equation, and through that I can play with the equation, and equation will give me V by L, right? Okay. Now let's go different way. If you have inductor, is it too fast? Like this will be the last example. Are you following this, right, till now? Okay, now somebody can tell me what is going to happen at I1 0 plus for this. Okay, What about I2 0 plus? So one of the component will be open, one of the component will be short. So at I1 0 plus, which one, like capacitor will be short or open? Short. If it is short, it is like this is already minus, so it will be V by R, R1, right? In another way, and this will be open, right? So it's open, so there is nothing is happening. So what will be I2 of t? 0, right? So those things you can write down, and it matches with what book is suggesting. No problem. Now infinity. At infinite time, it's a reverse. Whatever was open circuit, it's short. Whatever was short, it was open circuit. And you can find out it's V by R1 plus R2. Now you know all the differential equation will have I0 plus and I infinity and I prime 0 plus. You know how to find out those things. This is only possible if you are following mesh analysis or nodal analysis to find out the prime. Yeah. And once you have the complete equation, then you have to, okay, if you are getting such equation, then what are the poles you are looking into your system? Okay, I should have written not this one, it has to be V out. Do you have any poles or no? No, no, look, these will be zeros, not poles. So I'm asking, there are no poles, right, in this system, and you know where the zeros are, right? Can you see the zeros? Wherever it is. And of course, such kind of system, if you have differential equation, you know what is the complete solution and integral, particular integral, right? Through that you can find out v0 plus, v0 minus, and prime of 0 plus. Using all this, you can tell whatever you could have done with the Bode plot. You can talk about phase margin. Can you tell me what will be the phase margin of such system? Phase margin is 0 degree, by the way, because there are two poles. Sorry, I made it mistake. There are two zeros, right? So in that case, 0 is going to give you 0 to 1 0 is going to give you 0 to plus 90 degree. Two zeros are going to give you 0 to plus 180 degree. So answer is minus 360 degree. Sorry, plus 360 degree. That's the phase you are going to see. Now, the interesting part is how to do it in in the case of actually using whatever you learn in differential equations. What generally people are following, if they don't know Bode plot, then they are following same thing. But what they are doing, when this switch is on, if there is a network like this and this current is like this, and if you are doing such thing, then you can write down v of t or v of j omega 0 in terms of I, and I0 divided by y of j omega 0. What is y of j omega 0, by the way? Have you taken this notation ever? Y. Okay. This is known as admittance. Okay. It's reverse of what it's, yeah, the it's similar to transconductance, but transconductance is only one value. This is actually with respect to frequency. It's do you know the difference between these two, impedance and resistance? What is that?
Both complex.
Both. So similarly, that is the difference between transconductance and admittance. That is what we have written in terms of j omega 0. When you are going to solve it, it's I current which is flowing through the combination of R and C, series combination, which I am going to keep it here, and I am going to find out the magnitude of the response. I'll find out phase of the response, right? Phase is already known to you, tan inverse omega by whatever we used to do. And I can write down the output, which is here. I'm rename it as Vp of t is equal to the magnitude times sine omega 0 t. That's the already signal which was here already. So it's I sine omega 0 t. Let's imagine that, where I is the amplitude of the current. Now minus y. So that's the equation written here. It's same thing, it's a complex number, and this is what we are going to use it everywhere. Till now, any problem, just let me know. If you need some revision or something, because these are the things I was expecting from you to already know. Right? If you forgot, please go through it. Differential equations, please go through it, right? At least once. Although we are not going to deal with differential equations, we are going to deal with Laplace, only Laplace or maybe Fourier. But it will be a very bad foundation. Sometimes if we need differential, then it will be difficult, right? In future, you cannot say that I forgot this.